Hi, I'm Keenan Crane. I'm a professor of computer science and robotics at Carnegie Mellon University, and today I'm going to talk about how expanding our definition of a triangle mesh can provide lots of new opportunities for geometric computing. And the story really starts with a story about 19th century mathematics. So back then, if you wanted to talk about a shape like a surface, you'd have to describe how it gets embedded in space. In other words, you'd give it a so-called extrinsic description, like a parameterization. But a big development by Gauss and Riemann and others was to realize that there's a whole lot about geometry that doesn't depend on the way a shape sits in space. And so you can toss out this embedding and instead work with a purely intrinsic description like an atlas of charts. Okay? And so this ability to work with geometry without having to think about how it sits in space, even though that seems like a totally ordinary idea to us now, at the time that was a real revolution in the way that we think about geometry, leading in the 20th century to some pretty important discoveries like Einstein and Hilbert's work on the theory of general relativity. Okay, so what about the computational side of things? Well, right now, most people who work with geometric data, so programmers and engineers and so forth, typically think of a mesh as being given by extrinsic data, like vertex positions in three-dimensional space. Okay, so this is an extrinsic picture because it depends on how the shape is embedded. And instead, today, I want to think about a different picture, the intrinsic picture, where we throw away the vertex positions and just store the edge lengths of the mesh. Okay, so if you're a mathematician, you might already call this object just a triangulation, but for clarity, I will call this an intrinsic triangulation because it captures only intrinsic data about the shape. For instance, how far is it from point to point along the surface, but not how does that shape sit in three-dimensional space. Okay? Actually, where this all gets really interesting is when we have an interplay between intrinsic and extrinsic descriptions of shapes. So for instance, I can take an extrinsically defined polyhedron, like this cube, and I can triangulate the underlying space in many, many different ways, right? So now, even though I have triangles that appear to be extrinsically bent on my cube, well, as long as those triangles don't contain any vertices, they can be unfolded into the flat plane without any stretching. And those triangles can still be described by just three ordinary edge lengths. So again, this intrinsic triangulation sitting on top of the cube is given by ordinary connectivity graph plus edge lengths. Okay? So the rough idea is we want to allow bent triangles that are still intrinsically flat. What's so nice about this is that we now have the freedom to take our surface and triangulate it in all sorts of different ways without changing the geometry at all, which, as we'll see, opens up a world of possibilities that we didn't have in ordinary geometric computing. But to take advantage of this mathematical perspective, we also have to think about some computational issues. In particular, what are good data structures for keeping track of the correspondence between triangulations? And once we have those, how do we build useful algorithms on top of those data structures? And that is what I will talk about today. Now, one natural question to ask is why? Why is it useful to draw one triangulation on top of another? And I'll try to motivate this from three different angles. So from the perspective of classical computational geometry, you might imagine, okay, let's say I have a triangle mesh in the plane, some input triangulation, and I want to improve its quality somehow while preserving the original vertex set. Well, that's not too hard. I could start flipping edges, for instance, until I get a so-called delani triangulation. But if I force you now to preserve not only the vertices of the input mesh, but also the edges of the input mesh, and I say, please make this a better mesh, well, this is really annoying. There's not much I can do other than to maybe start refining the mesh to get better triangles. Okay? And this annoying situation is exactly what we're always faced with in 3D geometry processing. If I want to exactly preserve the input geometry, you're forced to preserve both the vertices and the edges of the input. And so basically, the only option you have is to refine the mesh to improve it. Okay? Or is it? Right? So what we'll see later on is that this intrinsic perspective basically lets us use the polyhedral surface as the background domain for computation rather than the Euclidean plane. So what that allows us to do is sort of translate a lot of classical algorithms from 2D computational geometry onto three-dimensional surfaces. And we'll talk about a few of those. Another angle is scientific computing. So here we might be using our mesh to solve a physical equation like some formulation of elasticity, and the challenge is that the mesh now must serve two conflicting goals. One is to just describe the geometry of the domain, and the other is to describe functions, a basis of functions that we use to represent the solution to our physical problem. So it kind of feels like a no free lunch situation. Our input mesh is a concise description of the exact geometry of the domain, but it may have very poor element quality. We can refine this mesh to get better elements, but now the size of the mesh blows up, here by a factor of 100. Or we can retain a nice small mesh with nice elements, but now the geometric quality suffers. Okay? And this is a nice thing about the intrinsic viewpoint. In the intrinsic setting, we can decouple the basis functions used to represent the geometry from the bases used to encode our function spaces. And even though our geometry is piecewise linear, one can, of course, still use any basis function with a triangular domain, so maybe like quadratic Lagrange bases. Okay, so now we kind of get the best of all worlds. Our intrinsic mesh perfectly preserves the input geometry, it has good element quality, and the mesh size stays pretty reasonable. The final angle, and the one that I'll talk about most in this talk, is geometry processing. So one observation we can make about a lot of geometry processing and shape analysis is that it's often expressed in terms of intrinsic data, maybe because we care about things like isometric deformations of shape. For instance, the Laplace-Beltrami operator, delta, is absolutely fundamental to geometry processing in the same way that the FFT is fundamental to classical signal processing, and it is intrinsic, as are the harmonic spectrum, the Gaussian curvature, the geodesic distance, Wasserstein distance, functional maps, and all sorts of other things that we know and love. So given that we want to work with intrinsic objects, why then would we try to process the mesh from an extrinsic point of view? Another big challenge is that geometry encountered in real data sets can be really, really bad. So to quote Jean-Paul Sartre, hell is other people's meshes, right? And if you've ever worked with real data, you know that this is true. So the bad news is that data just keeps getting worse and worse and worse over time. For instance, as we start to see, more user data from scanning and 3D printing. So this is a problem that's not going to resolve itself. We really need a way to help users of geometric software abstract away the mesh so that they can just focus on the geometry. In numerical linear algebra, there's a nice idea that helps with this kind of thing. So if you have a badly conditioned system, you might apply first some transformation, like a permutation. Then you get a better system that you can solve using algorithms that are not particularly robust, then invert this transformation to get the final solution, right? And the beauty of this idea is that it can be encapsulated in sort of a black box that the user doesn't have to think about. They can just type / in MATLAB and everything works out. Okay? So we'd like to do something similar for geometry processing, and the intrinsic perspective helps with that. Okay, so now what we can imagine doing is taking a bad mesh, doing an intrinsic retriangulation to get a better mesh, run some existing geometric algorithm that's not particularly robust, get our solution, and then transfer it back to the input mesh. Okay, so this way, as before, we can encapsulate this robustness in kind of a black box or a subroutine, and the user can just forget about all these meshing issues and focus on the shape that it represents. Okay, so hopefully that sets the stage a bit. To give a quick overview, today I'm going to talk about a little bit of history of intrinsic triangulations and then dive into two recent data structures we've developed, both signposts and one based on normal coordinates. And tomorrow we'll see more applications, including a new discrete Laplace operator and algorithms for computing geodesics, as well as a list of some really interesting open questions. To give just a few highlights, we're gonna, over these two lectures, develop some very fundamental surface meshing algorithms with quality guarantees, so basically extending delani refinement and constrained delani triangulation to surfaces. We'll have extremely robust algorithm for injective mapping that's enabled by an integer-based encoding of correspondence. We'll develop a Laplace operator that works for general non-manifold triangle meshes and even point clouds that provides kind of a bridge between mesh processing and point cloud processing. And finally, we'll have a greedy edge flip algorithm for computing geodesics, very much in the spirit of the delani edge flip algorithm that kind of unifies computation of geodesics and retriangulation of the surface. Before going any further, I want to acknowledge that all these great new developments would not be possible without my collaborators, so Mark Gillespie and Nick Sharp, who are my current PhD students at CMU, Yusuf Solomon, who is a former undergrad, and Boris Springborn at TU Berlin, not to mention all of our very generous funding sources. Okay, so what are intrinsic triangulations and where did they come from? Our first mental cartoon, again, is that we want to allow triangles that look bent in space but are flat intrinsically. In other words, they're still captured by just 3 edge lengths, and which define an ordinary Euclidean triangle. Okay? So we want these bent triangles, but they're still intrinsically flat. So a little more broadly, we have this kind of hierarchy. Okay, so we start out, and normally we just think of extrinsic triangulations, where edges are straight segments in Euclidean space. We can talk about geodesic triangulations, where we trace straight paths along the input polyhedral surface. But more abstractly, we could just think of a triangulation as a disjoint collection of triangles, which are identified along edges of equal length. Okay, and this final class really is strictly more general than the other two. Right? So not all intrinsic triangulations are geodesic triangulations. For instance, here is a perfectly good metric space made by gluing together Euclidean triangles, right? But it can't be embedded in R3. If I try to fold up these flaps, they're too short to meet. Okay, so this one definitely doesn't come from a polyhedron in R3. More precisely, we'll say that an intrinsic triangulation consists of a topological triangulation K of a surface with vertices V, edges E, and faces F, plus a discrete metric, meaning just a length for each edge that satisfy the triangle inequality in each face. Okay? Now, importantly, we will not require that K be a simplicial complex. For instance, it's fine if 2 edges are glued together, or if all 3 vertices of a triangle are the same. This turns out to be incredibly important for making sure that algorithms work in general. So formally, we could say that K is a delta complex, meaning a manifold 2CW complex with triangular faces. Even though we no longer have vertex positions, we can of course still compute basic geometric quantities from lengths. So for instance, if we wanted the angle at a corner, we could use the law of cosines. For the area, we could use Heron's formula, and so forth. Geometrically, the data we have describes what's called a polyhedral cone metric. In other words, a space that has 0 Gaussian curvature everywhere except at the vertices, where the geometry is indistinguishable from a circular cone. Right? Since each pair of neighboring triangles can be flattened into the plane, there really is no intrinsic curvature along the edges. And so an extremely important mental cartoon is to smooth out the edges and just leave the vertices. Okay? And so the critical point here is that we could have described this same space with many different triangulations. From the intrinsic point of view, there's absolutely nothing special about the one that we started with. So remember, historically, the progression was from extrinsic geometry, like parameterized surfaces, to intrinsic geometry, like Riemannian manifolds. And that perspective was really necessary to develop some big ideas in geometry and physics, like relativity. It's very appropriate then that some of the very first work on intrinsic triangulations was done in an effort to, guess what, solve Einstein's equations of general relativity. So here's a paper by Tullio Regge from 1960, and it's pretty remarkable how much it resembles our modern way of thinking about discrete differential geometry. In fact, it's even motivated by solving equations on a computer. So you could also think of it as one of the very first papers on geometry processing. Digging a bit deeper, we find that Regge was exploring this idea of intrinsic triangulations and came to all the same conclusions we did at the beginning. So he says all the data we need is the connectivity and the edge lengths. The particular choice of edges actually isn't that important, and the edge lengths are what give us our discrete metric. Okay, so here's a little bit broader history of intrinsic triangulations, starting with Alexandrov's proof that any convex polyhedral metric can be embedded on R3, going through lots of work by Thurston and others on using triangulations to understand 3 manifolds, and then a gradual buildup of tools for working with polyhedral surfaces, which I'll go through in a little bit. But the main thing to notice is that so far we haven't seen that many practical algorithms that use intrinsic triangulations. And the reason for that is that we're still missing some very basic ingredients. So one of the most basic ingredients is something called an intrinsic edge flip. This is something that's used in pretty much all of these algorithms. So rather than connecting vertices by a straight line segment through space, right? If I want to flip this edge, normally I would connect the opposite 2 vertices by this Euclidean segment. Instead, what we're going to do is trace out a straight path along the surface. And the very important fact is that this intrinsic flip leaves the original geometry completely unchanged. Okay. Building on top of intrinsic edge flips, one very useful thing we can do is construct an intrinsic delani triangulation. So the delani property is something that generally ensures good behavior of a lot of geometric algorithms. And it has many equivalent characterizations. In the intrinsic setting, the most natural thing is just to say every edge must have an angle sum, an opposite angle sum of greater than pi. Okay? And something that's really nice is there's an easy algorithm to always construct such a triangulation. If you see an edge that's not delani, you simply flip it, and you keep doing this until there are no more edges to flip. So one useful fact, it turns out, is that you can always flip a non-delani edge. This is always a legal operation. And more importantly, there's a theorem that says this algorithm always terminates. So you can always flip to an intrinsic delani triangulation using a finite number of flips. On top of intrinsic delani triangulations, we can then build what's called an intrinsic Laplace operator. So the Laplace-Beltrami operator delta is absolutely fundamental in geometry processing. It's even been called the Swiss Army knife of geometry processing. And Bobenko and Springborn define a very nice intrinsic Laplacian. So the idea is you just flip to the intrinsic delani triangulation and then build the usual cotan matrix or finite element stiffness matrix. A very useful fact is that the cotan weights are non-negative in a delani triangulation, right? And 0 only if you have a concyclic pair of triangles, right? All 4 vertices on a circle. In this case, the choice of delani edge is ambiguous. So what that means is that there's a canonical Laplacian on every polyhedral surface that doesn't depend at all on the input triangulation. And it always provides what's called a maximum principle, so no spurious extrema in your solution. In practice, this Laplacian behaves a lot better for all sorts of algorithms in geometry processing. Here's one example, for instance, where we want to compute geodesic distance by solving partial differential equations using something called the heat method. So here, if you plug in the intrinsic Laplacian rather than the ordinary extrinsic Laplacian, you immediately, without doing anything else, already get a lot better results. Another thing that has really motivated the development of intrinsic triangulations is computing discrete conformal maps. So conformal maps are widely used for texture mapping and fabrication and machine learning and all sorts of things. And there's a discrete definition of what it means to be conformal, which is that two discrete metrics are discretely conformally equivalent if the length cross ratios C are preserved. So these length cross ratios are literally just that. You take the product of opposite lengths in this diamond and take their ratio. Okay, so the problem then is given some triangulation with a metric and maybe some target angle defects, you want to find a conformally equivalent metric with either 0 angle defect or these prescribed ones. And the algorithm kind of flows the metric toward this flat metric, and eventually you'll be able to lay this out in the plane. So a nice theorem, which has finally been developed after many years, is that this is always possible. You can always discretely uniformize any input triangulation as long as you allow intrinsic edge flips along the way. And we'll talk a little bit more about that later. Okay, beyond that, I can't really think of a whole lot of other real algorithms that use intrinsic triangulations. There's a method of surface parameterization based on circle patterns. There's a method of embedding metrics into space, convex polyhedra into space. There's a metric of field-aligned parameterization, a few other examples, but that's really about it. There's really not much more use so far of intrinsic triangulations in practical geometry processing. So why is that? If this is such a useful perspective, why are there so few practical algorithms? Well, one thing to notice is that all the algorithms we saw so far assume a fixed vertex set. The only operation we allowed was flipping edges. Whereas in classical geometric computing, of course, there are all sorts of operations, inserting vertices, moving vertices, splitting edges, and so forth. So that raises a natural question, which is, how can we implement a much broader range of algorithms in the intrinsic setting? And I'm going to talk about how to do exactly that. Okay. One quick note on visualization. When you see a picture like this, the black wireframe is indicating the input mesh, and the colored triangles show a new intrinsic triangulation sitting on top of that input surface. Okay. So let's look at some more sophisticated data structures for intrinsic triangulations that enable these additional operations, starting with something called the signpost data structure. And this comes from a paper with Nick Sharp and Yusuf Solomon. So historically, there are really just a few data structures for encoding intrinsic triangulations. You can use this basic data structure of just connectivity and edge lengths, and if you wanted to track the correspondence between triangulations, then you might use an explicit mesh that represents the common refinement, this overlaid data structure. So today I'll talk about two alternatives, the signpost data structure and one based on normal coordinates. This basic data structure is what we've talked about already. Right? A minimal encoding of an intrinsic triangulation would be to have just a list of the edge lengths and some topological mesh data structure that can encode a delta complex. Right? So a reasonable data structure might be something like a half-edge mesh or a signed incidence matrix. A little vertex face adjacency list is not going to cut it because there are triangulations that simply can't be encoded this way. Right? So here's a perfectly good triangulation of the torus made with two triangles and just one vertex, but this is not a valid simplicial complex. Okay, so this is a very easy data structure, but it has a huge limitation, which is that it doesn't encode the correspondence between the original and the new triangulation. Right? I have no idea from this list of edge lengths and connectivity how the intrinsic edges cross the extrinsic edges. Okay, but I can at least evaluate some basic geometric quantities from these edge lengths. So we talked about getting angles and areas, and generally the cost and accuracy of evaluating these quantities from edge lengths is not much different from evaluating them from vertex positions. It's important to keep in mind that using vertex positions to compute quantities on intrinsic triangulations generally doesn't make sense. So for instance, if I wanted to compute the length of this intrinsic edge, the distance between vertex positions is going to give me an underestimate. But I can still think of the embedding as a signal on the surface, and that can be useful for various algorithms. For instance, I can compute extrinsic minimal surfaces using the intrinsic Laplacian. Okay? To implement our basic edge flip, what do we do in the intrinsic setting? Well, one thing we can observe is that the 5 edge lengths of two triangles let us lay them out in the plane, right? So if we wanted to, we could lay them out in 2D, we could compute this opposite edge length, and we could just store that on our intrinsic mesh. It's useful to know that this edge flip operation is only valid if, well, first of all, the triangles form a convex quadrilateral. If not, we're going to kind of fold the triangulation over when we try to do this edge flip. And also the endpoints of both ends of the edge have to have degree no less than 2, right? Because if I have a degree 1 endpoint and I tried to do an edge flip, then what I'm going to end up with is a cone point inside a triangle. So this no longer is a standard Euclidean triangle that we can describe using just 3 edge lengths. Okay, so what if we actually do want to store the correspondence between two different triangulations? Well, an idea introduced by Fisher and colleagues is to track where the new and old edges cross explicitly. So we're going to explicitly store the common subdivision of the two triangulations using, let's say, a half-edge data structure. And we're going to mark each edge segment as either original, new, or contained in both triangulations. The crossing locations are then stored as 1D coordinates, what I'll call barycentric coordinates, along these edges. Okay? The good thing about this data structure is, well, first and foremost, it actually does encode the correspondence between triangulations. So if I have to interpolate a function from one triangulation over the other, I actually have the data I need. It's also guaranteed to always give us the right connectivity of the common subdivision, because all the choices we're making are based on combinatorics and connectivity and not about vertex positions. On the other hand, it only supports edge flips. That's the only operation we can do, and even those edge flips can't be performed in constant time. In general, it can be quite expensive to keep track of all these crossings as we flip and flip and flip and flip, and we have to store all these crossings. So in the worst case, even in this simple example on the right, we might have to store order n squared crossings. So to overcome some of these difficulties, we took inspiration from these signposts that you see all over the world, which tell you how far and in what direction to walk to get to a particular destination. Okay, so then the basic idea of this signpost data structure is to store at each vertex the direction and distance to each neighboring vertex. And this gives you sort of an implicit description of the new triangulation. We don't explicitly store the list of points where the two triangulations cross, only how to get from one place to the next. Okay? In more detail, the signpost data structure consists of, well, the same data as before, so topological triangulation K, a discrete metric L, but now we also store the outgoing direction of each half edge, right? Half edge meaning just oriented edges of our intrinsic triangulation. And we also possibly store barycentric coordinates for any vertices that we've inserted into the mesh. So that's a new operation that we'll add. But assuming that we don't insert any new vertices, the storage cost is now fixed. Anytime we need to know a crossing point, we can just evaluate it on demand in a lazy fashion, just trace out across the surface. Though, as we'll see, we actually rarely need to do this. Okay? So the key idea is that we're going to maintain kind of not just a description of the intrinsic metric, but also in a sense a description of the intrinsic tangent spaces. Okay. To encode these edge directions, how do we do that? Well, we're going to take a cue from work on tangent vector field processing and store a unit direction x at each vertex as an angle phi around the vertex cone. So for instance, to get the direction of the outgoing half edges, we would normalize the Euclidean interior angles so that they sum to 2 pi, and then just take cumulative angle around the vertex from some fixed reference direction. Okay. Importantly, this fixed reference direction will stay fixed for all time. So even as we're doing flips, we always imagine that we have this one fixed reference direction. Okay, so suppose that we want to find where an intrinsic edge crosses an extrinsic edge. Well, no problem. The signpost tells us what walk we need to take. So we can just grab the edge length and the edge direction we've stored and sort of walk across the surface starting at one of the endpoints. In other words, we can evaluate the discrete exponential map to get from one endpoint of the edge to the other, which algorithmically means we just do a bunch of little 2D ray edge intersections. Edge flips look very much the same as before, except now we have to just update these signpost angles as we flip, which is just a trivial calculation based on the new interior angles that we compute from the new edge lengths. Okay, so then one very important new thing we can do with this machinery is to actually add vertices to our triangulation. Right? So far we've just been talking about flipping and flipping and flipping. Now we can actually refine the mesh. So how do we do this? Well, here we really make use of the directional information. So let's say we want to insert a vertex at a point I. What we're going to do is just trace from any corner of the intrinsic triangle to I. Right? So we're going to walk along the extrinsic surface and see where we land on that original mesh. We then record the barycentric coordinates of this new point, insert it into our intrinsic mesh, and update the signpost angles by adding the interior angles to the incoming direction that we got from our trace. Okay. And from there, we can implement all sorts of other operations using the same kind of thinking. We update the connectivity, the edge lengths, the signpost angles to reflect whatever changes we wanted to make to our mesh. And the really important point is not so much the specific details of how this all works, but the fact that as we do this, we start to build up a full-blown intrinsic data structure that's kind of a lot more feature compatible with the standard extrinsic mesh, with a mesh that people are used to working with. And a nice thing is that we can hide all of this complexity of working with this intrinsic triangulation with a simple interface, right? So we can, rather than asking people to work out Heron's formula or the law of cosines every time, we can just write some routines that compute a triangle area or a angle at a corner or whatever. Likewise, all of this thing about tracing and updating signposts and everything can be encapsulated in little local remeshing operations like flip edge and insert vertex and so forth. And once we have this abstraction, geometric algorithms, mesh processing algorithms can just be implemented as usual. Right? You can write code that looks exactly like what you would write for an extrinsic mesh, except that you're calling out to these intrinsic subroutines. And that is exactly what we set out to do, right? To provide kind of a black box interface that improves the robustness of mesh processing. So we can completely hide this intrinsic mesh from the user. Now, sometimes we will actually need this intrinsic mesh, or actually the common subdivision of the original and intrinsic mesh, for, let's say, processing downstream, although this happens less often than you might think. So for instance, for visualizing a solution or a parameterization or something. Doing this is actually not too hard. It's an easy two-step process. So first, what we can do is trace out all the intrinsic edges over the extrinsic mesh, store the crossings, and then run some simple local algorithm on each triangle to emit the subdivision, with just a couple cases to consider. The very important difference between doing this at the end versus maintaining an explicit representation of the common subdivision all the time is that we don't have to pay the cost of maintaining these crossings during processing, right? We just have this kind of output sensitive algorithm. So if we compare the performance, we find that the signpost data structure can be around 20 to 30 times faster than explicitly tracking this common refinement half-edge mesh all the time. Not to mention that this explicit overlay idea only supports edge flip operations, right? Nobody ever said how to do things like vertex insertions. Now, one thing to realize is that always when you're doing geometric computation, floating point error will creep in somewhere, no matter what data structure you use. So let's consider kind of a pathological input, this near degenerate triangle mesh, where this is its true delani triangulation. With this basic data structure of just connectivity and edge lengths, even just flipping edges might end up in a situation where you violate the triangle inequality numerically. With the overlay data structure, you're guaranteed to get a valid topology, but you can actually get the wrong geometry. And with the signpost data structure, tracing an edge out from a vertex I to a vertex J might actually just fail to reach the neighborhood of vertex J. Okay, so I'm pointing out that all of these things can happen in theory, but in practice, they're all essentially nitpicks. All these data structures actually work really great on real data, even on some pretty terrible meshes. So here's a test of robustness. What we're going to do is flip to the intrinsic delani triangulation and then extract the common refinement. This test succeeds on 100% of ordinary meshes, so things you might find, for instance, in the Princeton shape benchmark or the Miles and Zorin dataset. And for the worst 3% of meshes in the Thingy 10K dataset, we needed to perturb near zero area triangles or use quadruple precision to get things to work out. Okay, so what is this dataset? This is a good representation of the kind of bad data that lurks out there in the world right now. So this is a dataset of 10,000 3D printing models made often by kind of non-experts. And if you zoom in on these models, you look and you think, wow, this is insane. Like, how could anybody make a mesh this bad? Right? These are really, really not made for doing any kind of mesh processing or simulation. Okay, but in general, apart from some really pathological examples, these data structures actually do work quite well. Okay, one open question, interesting open question. So far, we've assumed that intrinsic triangulations always include the cone points from the original surface. But what if we wanted to work with a coarser mesh with fewer vertices, right? If we want to do some kind of intrinsic simplification, this is a very important thing to do in geometry processing. Well, one nice observation is that our signpost data structure can already be used to encode any geodesic triangulation on the surface, even if the vertices of the triangles are not cone points. So we could have triangles that go around cone points, okay? And then there's a question of what to do. Like, how do we capture this information? So for instance, maybe we store an additional curvature 2 form that accounts for these cones inside triangles or whatever. One interesting geometric phenomenon that comes up in the setting is that it turns out a geodesic triangle on a polyhedral surface can't contain less than negative pi curvature. Okay, so there's still a lot of thinking to do about exactly how to handle this situation. Okay, so it's nice that we have these robust data structures, but to really make this black box idea work, we actually need some nice way of retriangulating the surface. And we'll consider 3 different triangulation algorithms. One is the delani flipping algorithm that we've already talked about. So this makes the mesh delani, but the angle and area distribution of triangles can still be very bad. So for that reason, we're going to extend the classic delani refinement algorithm to the intrinsic setting. This is going to give us guaranteed bounds on angles, but might still have bad distributions of areas. And then we'll also consider an intrinsic version of optimal delani triangulation, where we can kind of spread out the vertices across the surface. Okay, so just to recall, Lawsons' flipping algorithm says, how do we get a delani triangulation? Well, we enqueue all the edges, and until this queue is empty, we pop out an edge, we flip it if it's not delani, and if we did flip it, we should enqueue the neighbors because they might now have become non-delani due to this flip. If we do this on a pretty bad quality mesh like this guitar, well, what happens is all of the triangles do become delani, or all the edges become delani, but we haven't really done much to improve the angle distribution, right? This angle histogram looks pretty much the same. The Delani refinement algorithm is going to help us with that. So specifically, choose second algorithm says, okay, until the minimum angle is above some lower bound, we're going to flip to a Delani triangulation using the same Lawson algorithm, and then pick any bad triangle, any triangle where we have angle less than the angle bound. In this triangle, we're going to insert the circumcenter of the triangulation, and then we're going to flip again to Delani. Okay? The question we have to answer in the intrinsic setting is, well, what is the intrinsic circumcenter? If the circumcenter is contained in the triangle, it's no problem, but what if we have an obtuse angle? So now the circumcenter is outside the triangle. If we try to draw the extrinsic circumdisk, right, this doesn't help us. We can't put this red point in our triangulation. It's not even on the surface. So what we're going to do instead is draw this triangle in the plane, right, and then consider the vector that goes from the vertex to the circumcenter, and we can trace this vector out over the surface, over the polyhedral surface, using the discrete exponential map. And that tells us where to insert this new vertex. So that gives us an intrinsic version of this Delani refinement algorithm where we really do improve the angles. You notice here that the minimum angle is now no less than 30 degrees. However, the area distribution is still not great. So our final algorithm is to use optimal Delani triangulation where we allow the vertices to move around. Okay, and in the intrinsic setting, this means we're going to only allow non-cone vertices, inserted vertices to move. Otherwise, we'd be changing the geometry of the polyhedral surface. Okay, so how does this work? Well, until convergence, we split any edges that are longer than some maximum length, and we move all the inserted vertices to the weighted average of circumcenters. To do this in the intrinsic setting, we again find these vectors that point toward the circumcenters, average them, and then move along that direction, and finally flip again to Delani until we're done. So here's just an interesting example of the Delani flipping, just showing how completely different this intrinsic triangulation can be from the input. Here's some examples of Delani refinement. And the important thing about these examples is that now, no matter how bad our input mesh is, we can always just click a button and be sure that the triangulation we're working with, that the triangulation we're using for our processing has good angles, that we have a good quality mesh to now run our algorithms on. Okay, so this is again what we wanted to achieve, this kind of black box robustness. And finally, here's some examples of optimal Delani triangulation where the triangles have been nicely distributed over the surface, although now you notice that we don't get these hard angle bounds anymore. You might ask at this point, well, this is great, but can't you do the same kind of stuff with just traditional extrinsic meshing? So here's a little comparison. So on the left, we have our intrinsic Delani refinement. On the right, we have a very recent algorithm for refinement using more traditional restricted Delani triangulation. Okay, and for one thing, the latter can't provide hard angle bounds for polyhedral surfaces, right? There's just not this guarantee anymore. We also see that it produces a mesh that is about 10 times larger than the intrinsic one, using about 1,000 times as much computation, and also relies on a volumetric mesh data structure rather than just a surface mesh data structure. In the end, another thing is that it doesn't actually provide positive edge weights for the Laplace matrix. Because the notion of Delani in this extrinsic case is not the one that corresponds to positivity of these edge weights. So what's going on here? Why is it so much harder to do this extrinsic meshing? Well, it's exactly what we talked about before. In the extrinsic setting, we really have to juggle element quality and geometric approximation quality, right? And in the intrinsic setting, we can just focus on the quality of elements. If you're a computational geometry person, you can think, oh, well, the intrinsic thing is just like working in 2D in the plane. Right? I don't have to worry about approximating the plane well. It's just the plane. It's kind of a similar thing here. Okay. There are also extrinsic meshing algorithms that seek to satisfy the intrinsic Delani property, but again, the struggle between element quality and geometric error produces meshes that are generally way bigger and have way worse error bounds. Okay. Here's another interesting open question. So given the importance of Lawson's flipping algorithm, will it always be efficient for every mesh we throw at it, or could this be really catastrophically slow? So in the 2D case, it turns out this algorithm has a tight worst case bound of order n squared, but in the intrinsic case, as pointed out by Bobenko and Springborn, it's impossible to bound the number of flips in terms of the mesh size, meaning the number of elements, because we can just keep flipping further and further and further away from the Delani triangulation. So you can consider this twisted cube with progressively longer and longer diagonals. Okay. However, a kind of surprising empirical observation is that on a large-scale real-world dataset, the number of flips required is typically just a fraction of the number of edges in the mesh. Well, why would this be true? One reason we think is that for a metric that comes from an embedded surface, the longest intrinsic edge is actually bounded by the extrinsic diameter. So the hope is that you can somehow bound the number of flips in terms of the geometry of the mesh rather than just the number of elements in the mesh. Okay, but this question is still open. Okay, so let's finally look at some applications where this signpost approach pays off. In general, one natural question to ask is, how do we get a solution on our intrinsic triangulation back to the original mesh, this last step of our diagram here? Well, the answer is it really depends on what you're doing. For instance, if you're doing something like just computing the eigenvalues of a differential operator, like the Laplacian, there's really nothing to do. You just grab a better value of the eigenvalue that you computed on this intrinsic triangulation, period. In some settings, like computing geodesic distance, it makes sense to still copy values at vertices, right? Because for distance, the triangulation you pick doesn't affect the notion of point-to-point distance. Right? Sometimes you just want the value at a point. So let's say you're computing the Karcher mean of a distribution. Okay, well, just extract the location of that point. In some settings, like injective mapping, you might be able to flip back to the original mesh while preserving injectivity. This is something that was done in the circle patterns work. And finally, as a fallback, you can always construct the full overlay mesh, right? So if you wanted to actually visualize a function from the intrinsic mesh on the extrinsic one, then you can go ahead and do this, though usually this is kind of overkill. One application is finite element problems. So again, we still have an ordinary triangle mesh. We can still use ordinary linear basis functions. No need to change our solver code. Just build the usual mass and stiffness matrix. We'll get the same matrix density, the same performance, the same convergence guarantees, and so forth, but with better accuracy and stability. If we want, we can also still use higher order elements. So here's one example. We just want to solve a Poisson equation, Laplace u equals f. And if we do this on an extrinsic or intrinsic optimal delani triangulation, we find that we get about twice as much accuracy, even on this rather coarse mesh. Okay. Another example is computing geodesic distance. We mentioned this before. So here's an input mesh that you have no business actually computing anything on. This is a really awful finite element mesh. Here's the exact solution, the exact geodesic distance. And if we run this heat method on the original mesh, well, things really don't work out so well. We get a huge amount of error. If we now flip to intrinsic delani, things get quite a bit better already. And then if we just do a little bit refinement, so we don't even double the number of elements in our mesh, the error already goes down to 0.7%, almost the exact solution. Okay, so this is pretty sweet. We can also apply adaptive mesh refinement to our surface meshes. So we can, for instance, if we want to compute things like harmonic Green's functions or short-time heat kernel, which are often used in geometry processing, this is something where we have a lot more detail in one place than another. And it's nice that we can now apply these techniques from the plane to curved surface meshes. And even with all of our error estimation and rebuilding systems and so forth, we still get a significant speed up over kind of a naive refinement. Injective surface parameterization is another place where this intrinsic perspective can really help. So let's say we want to compute a harmonic map from a surface to the circular disk. If we apply the intrinsic delani triangulation, then we can already eliminate flipped triangles like this red triangle on the bottom left. And then if we further use adaptive mesh refinement, we'll reduce the geometric distortion near the boundary where it's the largest. This signpost data structure is also very natural for tangent vector field processing because it's all based on encoding the intrinsic tangent spaces. Okay, and in particular, in a previous paper, we show that there's kind of a flip-free property for the intrinsic delani triangulation. So if we consider the minimizer x of what's called the vector Dirichlet energy, something that measures the smoothness of a vector field, then it turns out that this vector field will be flip-free if we have the intrinsic delani triangulation. So you can think of this minimizer as a vector field that's kind of harmonic with respect to the connection Laplacian rather than the ordinary scalar Laplacian. And what this flip-free property says is, okay, if I've found this nice vector field and I transport all my neighboring vectors to the center, then the vector at the center will always be contained in the convex cone of the neighbors. Okay, and so this is nice in practice because it helps prevent fold-over in things like field-aligned parameterization and meshing. So here's just an example of computing this vector field on ordinary extrinsic mesh with no special Laplace operator, and you do get these flipped directions that really point in the wrong direction. And here's what we get on the intrinsic delani triangulation, where there's no flips anywhere. If we then try to derive other quantities like parameterizations from this vector field, we see that this really pays off. So if we just use the ordinary Laplacian on the ordinary extrinsic mesh, we get all sorts of distorted garbage, whereas the intrinsic delani triangulation really gives the right result. In general, the vector fields that we compute in the intrinsic setting will just be nicer and smoother. So for instance, if we just look at the smoothest vector field with respect to this Dirichlet energy, then if we flip to delani or we do delani refinement, we actually reduce this vector Dirichlet energy further and further. And so this leads to a nice open question, which is there kind of a vector version of Ripa's theorem? So Ripa's theorem in the traditional setting says, if you give me a function, a scalar function at vertices of a triangulation, then it turns out the delani triangulation gives the smoothest interpolation, where smoothness is measured by this Dirichlet energy. So the analogous open question is, if I minimize the vector Dirichlet energy on the intrinsic delani triangulation, does that give me the smoothest possible vector field? And this question is a bit hard to answer because there are actually many different notions of discrete vector Dirichlet energy. I know of at least 5 different ones. Okay, so in fact, we've actually found that for 2 of these, you can find a non-delani mesh where the vector Dirichlet energy of the minimizer is less than the energy for the delani triangulation, but in general, it's not clear what the answer is to this question. Okay, so let's move on now and talk about a more recent and very different approach to tracking intrinsic triangulations, and this is work with Mark Gillespie and Boris Springborn. Okay, so we've already seen a few different data structures for keeping track of the correspondence. One is to explicitly store the common subdivision as a half-edge mesh at all times. The other is to use these implicit signposts, right? This explicit representation was nice because we always got the combinatorics correct, but it was expensive to track it all the time. These signposts were nice because, conversely, they're cheap to keep track of. It's this implicit representation, but they can fail due to floating point error during these tracing operations. So normal coordinates are going to offer the best of both worlds. We're going to get the exact combinatorics of the common subdivision, but it's an implicit representation. We don't explicitly know where all the crossings are at all times. And so that means it's an output-sensitive algorithm. The work required to extract the common refinement at the end is just proportional to the size of the output, and not all the intermediate operations. To understand how this all works, it's best to maybe start by just thinking about a single curve. So the basic idea of normal coordinates for curves is to just count how many times a given curve on a surface crosses each edge. And so for all edges that don't get crossed, we just store 0. Okay, so I'll use n to denote these normal coordinates. Okay, we're going to make one very important restriction, which is that this curve is not allowed to enter and exit through the same edge of a triangle. And that's what we'll call a normal curve. These normal coordinates were originally developed to study not curves, but rather surfaces embedded in 3 manifolds, and they show up in several different places. So for instance, in topology, you might use normal coordinates to study what's called the mapping class group. So every surface has all sorts of interesting automorphisms, like this Dane twist that maps the torus to itself. And if we apply this automorphism to a triangulation, then an element of the mapping class group can be identified with a path in the flip graph of the triangulation. Okay, so that's pretty cool, and that's just kind of the tip of the iceberg. From the perspective of theoretical computer science, normal coordinates are sort of a way of compressing curves. So the number of bits you need to store a really long, winding curve is much, much smaller in normal coordinates, and you can think about how to do operations on curves in this compressed format, almost like, fully homomorphic curve encryption. We're, of course, most interested in geometry processing. We're going to get a robust data structure for tracking intrinsic triangulations. And one important thing, we're going to think of normal coordinates more geometrically than topologically. So we're going to always imagine that they encode geodesic curves on a polyhedral surface rather than normal curves on a topological surface. Okay? One basic observation we can make is that as long as our curve doesn't stop or start at any vertex, the normal coordinates will always satisfy the triangle inequality. Okay, so 2 plus 1 is equal to 3, 4 plus 3 is greater than 5, and so forth. Why is this true? Well, it's pretty easy to see that at most, arcs that go into the first two edges can come out the third edge. In general, we will allow curves to stop and start at vertices, and here we have two useful numbers. So we can keep track of the number of edges leaving corner K and the number of edges crossing corner K, which we'll call E and C respectively. And you can get a feel here for the kinds of little formulas that we use when working with normal coordinates. So the kind of remarkable and useful thing about normal coordinates is we can go the other way. Given just the number of crossings on each edge, we can actually recover the curve itself. So how does this work? Well, you can imagine each time we enter a triangle, we have a few different cases where we're basically trying to figure out, okay, should we go left or should we go right or should we just stop at the opposite vertex? Okay, and we can turn this into a little algorithm. So this tracing procedure is pretty simple, but so far it actually just gives us combinatorial information, which sequence of edges is crossed by the curve. To actually get the geometry of the path, what we can do is then just lay out the strip of triangles that we pass through in the plane and just draw a straight line between endpoints. We know that this line must be contained in the triangle strip because, well, we know exactly which edges we crossed. We didn't cross any of the boundary edges of this strip. Okay? And so then to get the geometry, we just find intersections with each edge with this straight line. And we'll store those as coordinates between 0 and 1 along both the blue edge that we've traced out and each of the black edges. Okay? What's nice about this approach is that we're guaranteed to get the right edge sequence. All of our tracing decisions were made based on integer data. The only possible error that we could have due to floating point is in these line-line intersections. So we might get these barycentric coordinates slightly wrong. Okay, but in the absolute worst case, we can just clamp to 0, 1 to make sure that we still get a path with the right combinatorics. This is very different from the situation we had with signposts, where a trace could in principle fail to even enter the neighborhood of the vertex we're trying to hit. Right? Okay, so far we've been using normal coordinates to encode a single curve, but there are a couple nice observations we can make. Well, first of all, if we have a union of disjoint normal curves, then their coordinates, their normal coordinates, are just the sum of the individual normal coordinates. Second is that the edges of an intrinsic triangulation are just disjoint geodesic arcs, hence normal curves. Okay, so what that means is we can actually encode an entire triangulation with a single set of normal coordinates. Pretty cool. As with edge lengths, these normal coordinates can be updated using just a little local update rule. Okay, so the simplest case is if no curve terminates at a vertex, then we can just use a little formula that kind of looks like a tropicalized version of Ptolemy's relationship for the edge lengths in a cyclic quadrilateral. If we know that our normal coordinates come from a triangulation, then we can generalize this formula to the case where curves start and stop at vertices. Okay, so this all sounds pretty good. We can track correspondence, we can do edge flips, but actually it turns out that if we want to know the correspondence between these two triangulations, normal coordinates are not enough. And the reason is that after performing a bunch of edge flips, weirdly enough, you might have two intrinsic edges that have the same endpoints. So like on this octahedron, these two highlighted edges both start and stop at I and J. So if you trace one of these two edges out, how do you know which logical edge it corresponds to? And the solution we propose is to use something we call roundabouts. So the idea is that at each vertex of the extrinsic mesh, we're going to enumerate the outgoing edges in counterclockwise order. Okay? And then each directed edge or half edge of the intrinsic mesh is then going to point to one of these extrinsic edges. It's going to store the index of the next outgoing edge. And the naming here is kind of analogous to signs on roadways, on roundabouts or roadways that are telling you where to exit. Okay? If you stare at this for a minute, what you come to realize is that actually these roundabouts are kind of a combinatorial analog of this idea of signposts. So with signposts, we stored a floating point number that told us the outgoing angle. Now we're storing an integer that tells us something about the nearest outgoing edge. Okay? Once we have this data structure, we can extract correctly the common refinement of the extrinsic and intrinsic mesh, which is needed for something like texture mapping. Okay, so after tracing out all the edges, we just do something similar to what we used for signposts. We find all the intersection points, we connect those intersection points up into segments within each triangle, and then we extract these polygons. The difference is that the connectivity we get is always correct. The ordering of these intersections is always known exactly from our combinatorial tracing operation. The application that really motivated us to do all of this is discrete conformal mapping. So conformal mapping or uniformization is a really powerful tool in differential geometry that allows you to construct a canonical map to a domain of constant curvature, or more generally, a domain that has maybe a few isolated cone singularities. So you can imagine taking this head and mapping it to this sort of cuboid that's flat except at the corners. Once you have that, you can cut it open and lay it out flat in the plane. A very important result is that this smooth classic uniformization theorem has a perfect discrete analog. So actually every polyhedral mesh, no matter how awful the input triangulation is, can be uniformized in an exact sense. And this is really important for robust geometry processing. It means we have this kind of guaranteed mapping algorithm. So this is a problem with a long history with lots and lots of contributors, and also some very nice connections to hyperbolic geometry. So very recently, we have a new paper on this topic that resolves, let's say, some of the lingering practical difficulties with actually computing these maps. So for one thing, it uses this scheme based on normal coordinates and roundabouts to get robust tracking of correspondence. It gives a very nice way of interpolating texture coordinates using the light cone model of hyperbolic geometry. It handles the case of mapping Gina's zero surfaces to the sphere, which wasn't done in previous algorithms. And finally, it takes advantage of a nice observation that vertex scaling commutes with so-called Ptolemy flips, which simplifies optimization. And this really seems to be the right computational approach. In fact, there is another paper by completely different authors that was done concurrently that takes this exact same approach. Okay, so to continue with the story about robustness, in practice, it's not enough to just compute an intrinsic description of this flattened surface. You actually have to extract the mapping between the different triangulations. And in theory, this is no big deal. Okay, all you have to do is construct the common subdivision of three triangulations: the input mesh, its intrinsic delani triangulation, and the uniformized or flattened mesh. Once you have that common subdivision, you can compute projective texture coordinates at the vertices of this common subdivision. In practice, unfortunately, you can't escape the difficulties of floating points. So all the proofs of correctness that this all just works out easily assumes that you're working with real numbers. And so this is a case where if you really push things, then even the signpost data structure will break down. And these normal coordinates are really, really necessary. Okay. And this is especially true because now we're intersecting not just two triangulations, but actually three triangulations, all on maybe some really bad input. Nonetheless, with these normal coordinates, everything works out beautifully. We can texture map the absolutely worst meshes that you can possibly throw at it. So we get the right result even if we have totally crazy configurations of cone singularities and if we have totally awful triangulations like coming from this thingy 10K data set. A major shortcoming of normal coordinates so far is that we really only know how to perform edge flips. But for geometry processing, you also need other operations like vertex insertions and edge splits and so on and so forth. So these are things that are not maybe typically needed for topology, where maybe you're happy to just work with the coarsest triangulation. So we're currently working on turning normal coordinates into a full-blown practical data structure, and the preliminary picture looks pretty good. For instance, we can recover the common subdivision not only after delani flipping, but in fact also after delani refinement, which is much, much harder. And here things work a lot better than with this signpost data structure. Okay, so the point here is to just really push the boundaries of robustness on these data structures more and more and more, so that people working with geometric data can spend less time getting frustrated about meshes and more time making beautiful discoveries. Okay, so that's it for today. Next time, I'll talk less about data structures and more about actual algorithms that we can run on these data structures. Thanks.